So the way we got to LU factorization was to look at the problem of solving simultaneous linear systems. And that actually turns out to be a really important problem. And it's important enough that when people use a library routine that implements this operation, they demand extremely high performance. Okay? So how do we attain extremely high performance? Well, we could go and carefully implement LU factorization exactly the way we did for matrix-matrix multiplication, as was explained in one of the enrichments in week 5. But you can only imagine how complex that particular implementation would become. And if you had to do that for every important operation that's out there, this would be a major strain, and then it would have to be tuned every time a new architecture came out. So what do people do instead? Well, what people do is they cast computation in terms of matrix-matrix multiplication. And what we're going to look at now is how to cast most of the computation that is involved in an LU factorization in terms of matrix-matrix multiplication. How do we do that? Well, the important thing is that instead of repartitioning the matrix exposing a scalar here on the diagonal, which then meant that the pieces above and below were column vectors and to the left and to the right were row vectors, what we do instead is we pick up a small block. This block may be of size b by b. It's important that it's square, because that means that as we go through the matrix, these blocks are always square, these blocks are always square, and we nicely identify pieces of L and U that are sort of hidden in A because they overwrite A, etc. Okay? So, this block is some square block. The blocking parameter is dictated by how the matrix-matrix multiply is optimized, again, as was discussed in week 5. And the question now becomes, okay, how do we come up with blocked algorithms? Well, it's no different than what we did when we looked at unblocked algorithms. Okay? We have a partitioned matrix expression. What's different is that we now march through the matrix in terms of blocks. But it's still a matter of just taking the repartitioned matrix and plugging it in there to come up with the state before the update step, the state at step 6. And similarly, it's just a matter of taking how the matrix is repartitioned and moved forward in order to determine what step 7 is. And then it's still a matter of comparing step 6 to step 7 to come up with what the update step must be. Okay? So, what I'm going to do is I'm going to go and take this and do this. The loop invariant that I chose is loop invariant 5. And the reason for that is that I happen to know that in the end will cast computation in terms of a matrix-matrix multiply that tends to be preferred because it gets slightly better performance. And what I want you to do is, while I'm working on this, I want you to go ahead and work on step 6 as well. And then we'll reconvene in the next video and we'll compare notes.